영상으로 수업을 좀 대체를 하고 다음 주 월요일부터는 강의실에서 수업을 이제 진행할 수 있을 것 같습니다. 여러분들 좀 양해 좀 바라고요. 저희가 지난 시간까지는 이제 이론 수업을 좀 마쳤습니다. 지난 시간에 빔 요소 그리고 프레임 요소를 사용한 유한 요소 해석의 이론에 대해서 이제 설명을 드렸고 이제 이번 수업부터는 이제 빔 요소 그리고 트러스 요소가 사용된 구조물의 구조 해석 실습을 좀 진행을 하게 됩니다. 아마 말미에는 이제 우리가 여태까지 배웠던 모든 요소들을 사용한 구조물의 해석 예제도 우리가 좀 재밌게 수행을 할 것 같아요. 제가 아직 목이 아직까지는 조금 안 좋아서 목소리가 조금 전과 다를 텐데 아마 다음 주에는 그래도 좀 많이 좋아질 거라고 좀 기대를 하고 있습니다. 네, 그러면 수업을 진행하죠. 그리고 이제 그 이 마지막 강의 자료는 LMS 시스템에 업로드를 했기 때문에 여러분들께서 확인을 하셔가지고 다운로드를 받으시면 되겠습니다. 네, 그럼 진행하죠. Okay, let's see. Obviously, the beam element is one of the line element. Therefore, it is not very difficult because we already discussed about the modeling and analysis for the line element used structures. So, when we use a beam element, we should define the additional geometric properties as well as the sectional area. So, one of the very important physical quantity is second order moment of inertia at the section here. So when we use Abacus program, you can use a library, the section library. Okay. So I mean, there are some predefined section of the line element like that from the box to T. If we define the I-shaped member like here, for example, as you can see here, let's see. Okay, this is the laser pointer. So when we define I-shaped section of the line member here, you can input the dimension of the section. So can you see it here? From I, we can input the thickness about the flanges and web. So once we input the values at here, this program can automatically calculate the required sectional properties from the section area to the torsional constant. If you select the box, for example, you can input the dimension related to the given box shape. This is very simple. Then we can input the uh, material properties as well as the sectional property. So we can define the elastic modulus, and you can calculate the shear modulus using this equation. This equation is come from the theory of elasticity. So G, the shear modulus, can be calculated by the elastic modulus and Poisson ratio. If we wanted to uh, include the density of the material, you can use this, the law. As well as the predefined section, you can directly input the calculated sectional properties like that. So if you select the general region here, then you can input the sectional properties like the sectional area, the second moment of inertia, product moment, and the torsional constant, J. When we define the beam element, we should clearly define the orientation of the sections. So as you can see here, obviously we can see the two perpendicular axes at the sections correspond to the sectional axis like that. This one and this one. The program can recognize the different second moment of inertia at the section. So, considering the primary axis at the section, you should clearly define the directional cosine of the first axis at the section. Okay, so can you see it here? 그 비묘수 쓸 때 제일 조심해야 되는 것 중에 하나가 요 섹션, 요 단면의 단면축의 정의입니다. 왜냐면 그 우리가 이제 요거보다는 이게 이게 훨씬 더 좀 클리어한 그림 되겠네요. 보시면은 이제 1번 축과 2번 축이 있죠. 그 단면에 두 개의, 그러니까 카테시안 코디네이트 시스템을 쓰게 되면, 직교좌표기를 쓰게 되면 두 개의 단면 축이 이제 정의가 되는데, 각 축에 상응하는 이제 I 값, 소위 이제 I 값이 다른 경우가 많죠. 요, 당장 요 그림만 보더라도 우리가 이제 단면의 효율성을 고려했을 때는 대부분 이렇게 한 축에 대한 단면 2.5m가 크게 설계를 합니다. I형 단면의 경우는 요 방향으로 향하는 축에 대한 모멘트가 이제 크도록 설계를 하게 되죠. 그래서 우리가 정확하게 요 축의 방향을 설정해 줘야 돼요. 요 섹션 프로퍼티를 넣을 때는 단면 그 이제 단면적하고 두 개의 I 값을 넣게 돼 있어요. 요 두 개의 I 값에서 첫 번째 들어가는 것이 1번 축에 대한 모멘트입니다. 그러니까 그러니까 그 휨으로 치면은 요 방향의 휨이 되겠죠. 그러니까 요게 회전축이 되는 휨 거동에 대해서는 I11이 대응하게 됩니다. 또 요 축에 대한 회전, 즉 요 방향의 그 모멘트에 대해서는 2번 축이 이제 관여가 되는 거죠. 그래서 요 섹션에서는 1번 축과 2번 축에 대한 물성을 집어넣는데 물론 이제 이것도 마찬가지예요. 여기 1번 축, 2번 축이 되는 거예요. 이게 1번, 2번 써있죠. 근데 문제는 우리가 그냥 단순하게 선만 이제 그리기 때문에 프로그램은 우리가 단면에 축의 방향을 넣기 전까지는 그 방향이 어떤 건지 몰라요. 그래서 요 1번 축, 단면의 1번 축에 대한 방향을 방향 코사인으로서 집어넣어줘야 됩니다. 그래야지 이제 프로그램이 인식을 하게 돼요. 어, 이 평면상에서 모델링하는 경우, 즉 이제 2차원 빔 구조를 모델링할 때는 어차피 1번 축은 이 면외 방향, 이 평면의 면외 방향으로 향하게끔 설정될 수밖에 없습니다. 그래서 이제 프로그램을 이제 쓰게 되면 0, 0, 마이너스 1. When we model the beam structure in 2D plane, the default uh, the unit direction cosine would be 0.0 minus 1 because every model will have the primary axis coincide with the outer plane of the given xy plane. So in 2D plane, we simply input the default value like the 0.0 minus 1. However, if we model the structure in 3D, then you should exactly input the direction cosine at the section of every members. Okay, so please mind that. So when we take the examples, I will explain this orientation again. Also, when we define the element in mesh module, we should apply the multiple mesh, right? Because we should take the smooth flexural deformation of the member. This is the different from the truss element modeling and analysis. When we deal with truss element, we should assign the single element for each line. But when we take the beam element analysis, you should assign the multiple meshes for every segment, okay, in order to obtain the smooth flexural deformation. When we take the examples, I also explain this strategy again. Then, so we should see the internal process of the beam element as well as the displacement at each node. But unfortunately, the default option about the output in the default option for the output observation, the section pulse and moment were not checked initially. So before text analysis, we should access the output request here. Then we should check the show pulse and bending moment as the one of the field output in the program. Also, we can see the various result from the displacement to the sectional, the internal process at the section. So, as you know, we can use the query option. Then you can click the, the specific location. Then you can find the calculated internal forces like the show force, the bending moment, as well as the actual force. As well as the query option, you can plot the XY graph, uh, checking the specific location over member. Then you can draw the graph about the selected output like that. Then you can also access the data by clicking uh, the generated graph. Then you can copy and paste about the result for your uh, request. Okay, so now we go to the examples. So if you are a little bit confused, you can refer to the previous slide when we use the abacus. Now let's see the first example. So this example is a very simple statically indeterminate beam structure. At here, the structure is subjected to the vertical force and moment. So when we model the structure, you may uh, assign the intermediate node here in order to assign this external load and moment. So I will model the structure dividing as the two segment, this one and this one. And then at the intermediate point, I will assign the force and moment. And this is a sectional property, no, this is a dimension of the section. So I'm using the predefined section library. We directly input the dimension values like that. And then the program will automatically calculate the sectional properties like here. So you do not need to calculate the values yourself. Our objective are shown like that. Firstly, we will see the structural deformation due to the assigned process at the moment. And also we can check where the maximum displacement is observed. And then we can read the values. Also, we can check the relation forces as support. So once you obtain the relation force and moment at here and here, you can check whether your analysis is correct or not by checking the force equilibrium. Also, we can check the internal process of the structure. Then let's see. The length is 30 feet. Okay. If you uh, uh, open the ABOX program, you can start from the part module. Then let's see together. So first of all, we will select the 2D planner because the structure can be analyzed in 2D. So obviously you can select this one. Okay. So if you select the 3D, you should clearly define the beam orientation at the section, as I mentioned before. Uh, as, although you select the 3D, you can see the same result about the example. And the base picture is wired. And please click continue. Now we will make the 30 feet beam structure. And as I mentioned before, here, we should assign the moment and the vertical force at here. So I will draw the two segment connected beam structure. So the first point would be O to O in my case. Second is RMC. What is the primary unit about the structure here? We will use inch for the length unit. Then the length would be 30 feet times 12 inch, right? And then the moment should be converted. The second point would be 노트북에서 뭐 이제 아바코스도 켜고 PDF도 켜고 아바코스 뭐죠? 줌도 켜고 하니까 조금 버벅대네요. 좀 양해 부탁드리고요. 응? 뭐야? 엑셀을 켰는데 안 켜지네. 그러면 계산기를 쓰겠습니다. Let me see. 음, 15 times 12 would be 180. And the last point would be 360 point0. 포인트 옵션이 있으니까 더 버벅대네. Okay, let's check again. So the length, total length of the structure is 30 feet. So 30 times 12 would be, let me see, 30 times 12, 360. So the model was correct. And then please click done. And now we go to the next module. Okay. 많이 반복되네요. Okay. First of all, please click the create section here. Then the beam should be selected. And here we will use a beam element. So please leave the default option and click continue. Then please check before analysis for section integration. Then you can directly input the material properties. Then please see before we take the material properties. Let's define the section by clicking this one. Among them, we will directly input the dimension of the section here and select I and click continue. Then you can directly input the values. Let's see the given values. So first of all, I is the distance between the neutral axis and the, the outer tip of the lower flange. Then I would be half of the entire height for this symmetry axis. So the height was 6, so I would be 3. And H height would be 6. B sub 1 is here, the width of the lower flange. B sub 1, B sub 2 are 4 because the section is a double symmetric section. T sub 1 is the thickness of the lower flange. So that was 0.6, 0.6. T sub 3 is the width or the thickness of the web. So T sub 3 is here, T sub W. Then click OK. Then you can input the Young's modulus. We will use pound for poles while the inch for the length. So you directly input this value. How about the shear modulus? The Young's modulus is zero point 0.2, so you can calculate the values. Okay. There was elastic modulus. G would be this one over 2 times plus, what is that? Okay, okay. Yeah. Is it correct? Let's check again. Okay, correct. The equation is correct. Oh, let me see. Let's check again. So we input Young's modulus and the shear modulus, and we define the sections. So you can find uh, the section profile at the left side tree. So please go to the left tree, and if you click this one, then you can see the profile one. So if we want to revise the sectional dimension, you can access this one, and then you can change the values. Then the sectional property will be updated. Okay. Then we can assign the defined values. See. Please click this one, and then select the member, click done. Then you can select the define the section model. Then uh, we should define the orientation of the section. So please recognize that this member is modeled in 2D. Then what is the direction of the first axis at section? That goes to the z-axis. So please click this one. Assign beam orientation and select the member. Click done. The default is therefore 0.0.1. So please push enter. Then as you can see, T means the actual direction or the longitudinal axis, longitudinal direction of the member, because we modeled the outline of the structure by defining the nodes. The program also already know the coordinate of the 2 points here and here. It means that the program will automatically define the longitudinal direction as a T here, and then we input the direction of the first axis at section like that. So 1 means the axis 1 at the section. So because we defined the two axes, like the two perpendicular axes, like the t and 1, the program now can calculate or define the remained the axis, right? Because the program followed the Cartesian coordinate system. 이게 뭐 수학적으로는 당연히 그렇죠. 두 개의 이제 직교 축을 정의한 거기 때문에 프로그램은 나머지 하나의 축은 자동으로 이제 결정을 하게 되는 거고, 제가 기억을 하기로는 오른손 법칙을 따릅니다. 그래서 요 방향과 요 방향 중에 오른손 법칙을 따라서 아마 요 방향으로 프로그램이 정의한 것으로 저는 이해를 합니다. Okay. So once we checked the defined axis, then you can go out this property module. Then please go to assembly. Now we're gonna record the prepared path by clicking the create instance here. Then please select path. Then you can go to the step. Here, firstly, we will define the analysis type. Like that. We already know that. Then, as I mentioned before, we should access the definition of the field output because we should check the section property and moment. So please click this one, the field output manager. Then you can access the predefined field output. So please take double click at here. Then you can find what physical quantities were already selected in initial stage. Among them, please click this one, force and reaction. Then we should click section property, section force and moment. Okay. Click OK. Then we're gonna go to the load module here. First of all, let's define the boundary condition. Please click the second option. Then click displacement and rotation and click continue. As you can see, we see 3 points because I draw the sections segment like that. And then first of all, let's define fixed boundary condition at here. So click this one and click done. Then please select every degree of freedom. Because we modeled the structure in 2D, you see 3D of freedom. The two are translate and one is rotation. UR3 means each rotation axis is a third axis. Third is a G, and G is out of plane direction. Now we will define another degree of freedom. Let's see the boundary condition here. So the point 3 is supported by the hinge. So please click this one again and select displacement rotation again and click and select this right side point. Then click done. Now we will check U1 and U2 and click OK. Then lastly, we will assign the force and moment. Let's see electron to gain. The force, firstly, we will define the vertical force. Then please click this one, create load, and concentrated force first. Here, click done. And among them, we will define CF2. So, seeing the positive direction of the global axis, and we will input minus 1000. Then you can see it like that. And next is moment. Let's see. The moment is 1,000 pound-feet. So please remind that we use inch for the length. So that would be 12,000 pound inch. Then please click this one again. Then select moment. Click continue. Select this one. And using our right side, the right hand side, right hand, please put the right thumb coincide with the positive G. Then you can understand the sign of the moment. According to our lecture note, this one would be positive 12,000. You see it? So as you can see, if we define the moment, you can see double arrow vector that indicate the direction of the rotating axis of the moment. Okay, so using your right thumb, you can feel the direction of the assigned moment. Okay, the remained four fingers will indicate the direction of the moment. And that Abacus also follow the right uh, uh, right hand rule. Then go to the mesh. Now we may take the effect of we may check the effect of the mesh assignment. First of all, I will assign the single element for each segment. So please click this one. Let me check. What? Let me see. Okay. So as you can see, if you input 150, nothing but the length of each segment, then you can see the single element would be assigned for each segment. Then please click this one, mesh part. Click yes. Then we're gonna see the assigned element by clicking assign element type. Select every segment. Click done. As you can see, the beam element was assigned as default option. So in Abacus, the beam element is the default option for the line member. So you do not need to change the element type. Then we go to the job. Let's take the analysis now. Click this one. Example. Then please click Job Manager to submit prepared model. 이게 이렇게 버벅될 수준의 모델이 아닌데 노트북이라서 조금 그런 것 같습니다. 그 우리가 이제 기말고사까지 수업이 한 몇 번 남았죠? 한 네 번, 다섯 번 정도 남은 것 같은데 그 시간 동안 충분한 아마 연습이 될 것 같아요. 네, 여러분들 그 중간고사 보셔서 아시겠지만 어쨌든 이제 우리가 물론 이제 시험을 위해서 공부를 하는 건 아닙니다. 명확하게 그런 건 아니고 근데 이제 하여튼 여러분들의 노력에 대한 결실은 결국은 이제 시험 성적 또 이 학점의 결과겠죠. 그래서 중간고사 때 조금 미진했던 학생들은 아마 그 시험 시간에 충분한 이제 여유를 가지고 모델링을 해서 결과를 잘 정리하는 것이 되게 중요하다는 것을 아마 이번 경험을 통해 아셨을 거니까 수업 시간뿐만이 아니고 여러분들이 좀 개별적으로 시간을 좀 내셔가지고 연습을 충분히 좀 해서 시험 때 당황하지 말고 이제 신속하게 모델링하고 해석 결과를 좀 분석하는 그런 연습을 좀 하시면 좋을 것 같아요. As you can see here, analysis was done. In order to access the result, please click the result here. First of all, we will see the deformed shape of the structure due to the applied exclusion. As you know, if we click this one, we can see the, the deformed shape. How about that? Is it reasonable or not? Because we assigned the single element for each segment like that, here and here, you can see those kind of desirable deformation, right? How to improve the result? We go back to the mesh module, then we will assign find mesh. So please go to the mesh again. Now we will revise the mesh definition. In our lecture note, let me see. Uh, we should see the structural deformation. Then is there any direction about the mesh definition? Actually, firstly, I will assign five elements for each segment. Then please click this one. Now you will if we divide 180 by 5, what the result? 3, so 3 and 6. 1, 2, 3, 4, and 5. Okay. So totally 10 elements was used for model the structure. Now we go click this one, generation again, then go to job, then submit. 돌아가는 것 같습니다. 컴퓨터도 버벅대니까 지금 이게 돌아가는지 안 돌아가는지 잘 알 길이 없네요. 돌아갑니다. submitted. running, complete. So please click result again. Then we will see the improved result. So click plot. How about that? Let's compare deformed and undeformed configuration. So the white line is the initial configuration of the structure. So as we know, the left side was fixed, while right side was supported by hinge. So in the left side, we cannot see the rotation. How about that? Can you because we defined the sectional shape by using predefined the library, you can take the rendering, go to the view and click ODB display option. Then you can click render beam profile. You can see the program will show us the shape of the member uh, applying the given dimension of the section. If we want to see more clearly, you can control the scale factor for this rendering. So for example, if you take 5, then you can see those kind of artificially enhanced the sectional dimension, okay, or to the original. Anyway, so as you can see, because of the defined boundary condition, you can see there is no rotation. How about the right side? Here you can see the rotation, but although the rotation is observed, the point is not moved. Right? And please remind that because we didn't assign any offset at the section, every quantities will be assigned to the centroid of the section. So you can see the displacement will be observed. You can see the displacement at the section here, but as you can see here in the centroid, there is no transfer rate. Okay. And still, the still the very smooth deformation is not observed. So we go to the mesh again, then I will revise the mesh definition again. So I assigned the totally 20 elements. And let's go to job, submit again. 지금 여기가 이제 학회장 근처에 호텔인데 호텔방에서 지금 수업을 녹화를 하고 있습니다. 그래서 저희 집이 아니고 그 일본은 확실히 이제 호텔도 되게 조그마해요. 약간 배기 조금 정신병원 같이 약간 뭐 허연 것도 아니고 푸르스름하게 보이나? 그래 보이는데 호텔입니다. 아주 조그만 비즈니스 호텔이에요. Okay. Because we increase the number of the elements, we can expect more smooth deformation. How about that? So, the in order to obtain the smooth deformation, we should assign the sufficient element to the beam structure for obtaining the more realistic structural response. Now, let me see the objective again. So first, the object was conducted, the fin sheet. Second, we will see the maximum displacement of the structure. And let's change the variable here. And we are gonna see the vertical displacement. Obviously, the horizontal displacement of those kind of simple fracture member is not important. So change U2 here. Maybe the maximum displacement will be observed near the point where the external load is applied. Then please click this one, contour option. If you click show location and maximum or minimum values about the selected output variables, you can see it where the maximum response is observed. So according to the result, the minimum, or obviously this is a maximum deflection. The minimum deflection would be observed at here. So the value is minus 3.65 inches. No, 5 point. Maximum deflection would be 3.649 inch. And now we check the reactions. So please change RF. As I mentioned before, in this example, the horizontal reaction is not very important. But in order to check the pulse equilibrium, let's briefly check the reactions. Let me see. So because we did not assign any horizontal force as the external load, you can see nearly zero horizontal reactions at here and here. Can you see it? The order is quite smooth. So we go to the next one. The RF2 is the vertical reactions. So maximum vertical reaction is observed at the left side boundary. The value is 248 times 10 power 2. Let's record the value. Reaction. North, left, left boundary, right boundary. At the left, the value is shown 7.2. Right, I will use query option. 275. Unit is what? In, in pound. Then let's check the pulse equilibrium. If we add the two values, we're gonna have 1,000. That is perfectly same with the assigned external load. Assigned external load was minus 1,000. So you can see pulse equilibrium is satisfied, although a very small value is remained. 뭐 요거는 뭐 충분히 우리가 그냥 무시해도 될 정도의 값이겠죠. Now we will check the reaction moment. So please change RM3 here. Then the reaction moment will be observed at the left side only. So please click. Okay. Obviously, you do not need to click the bell because this contour is already uh, shown. So the value was left. The unit is 12 inch. So also you can check whether this will satisfy the pulse equilibrium or not. Because I cannot draw the figure by using the simple mouse, I will skip the check the pulse equilibrium about the moment. In our classroom, we will check the moment equilibrium again. But let's check how to. I will explain how to check the moment. So we know the reaction forces at here and here, as well as the reaction force. We can also see the reaction moment at here. So what force and moment were existed? At here, we see the single vertical reaction and moment. Here, we see the vertical reaction. Here, we have the vertical force and moment. So, truly five force and moment compound were existed. So, if you check the moment equilibrium at everywhere, firstly, you will define some reference point where the moment is calculated. So, I mean, if you select this point, you may add the moment about this one, 12,000 pound inch, and the moment reaction at here, and the moment induced by the vertical reaction at here. As you can see, if you select the point here, this onward force will make the uh, clockwise moment. How about that? This force will make counterclockwise moment. So, totally five moment compound will be included in the equation for force equilibrium check. So you can check whether the moment equilibrium is satisfied or not. Then we're gonna go to the last mission. That is observation of internal forces. So if you select the internal force compound like that, first of all, SF means section force. As you can see, SF1 is, let me check. SF1 is actual force, and SF2 is a shear force. Please mind that. So although they have the number, the one and two, SF1 means the actual force at the section because there is no actual behavior. You cannot see the significant actual force at the section. How about the section, the shear force? If you select SF2, you can see the section force result. So checking SF2 here, please click query again. Then you can see the shear force result. Okay. If we click the specific node, you can see the section force result. Because there is no force at the intermediate point, not this point, you can see there is no change in shear force. However, due to the applied vertical force at here, you can see change in shear force. The vertical force will jump down in shear force. Can you see it? So the force, shear force would be the same with the reactions at here. By using this option, you can see the shear force. Also, you can see the section moment because we modeled the structure in the plane. You may see the single component about the movement. If you expand the dimension from 2D to 3D, you may see the three different moment. The two are the bending moment, and the one is torsional moment. And similar to the observation in shear force, you can click the point, then you can find the bending moment result. This is the first option when we want to see the result. And as you can see in our slide, you can use a XY plot option. So if you click this one, you can see the new dialog box, and then please click ODB field output, then click continue. Then we will see the internal force at unique or selected node. Then you can see the various structural responses, what can be observed in this ODB file. Then if you want to see the shear force, for example, please click SF2, then click plot, no, go to the element node. Now you may select the point where the moment the shear force is observed. Let's see here. If we want to see the shear force at here, for example, please click the point and then please click edit selection, then click plot. What that? You can see the result because we take the simple static analysis without any iterative steps, you simply see the result at time equals 1.0 because at the point because the point is subjected to the vertical force, there is shear force change. Okay? I mean the shear force was changed in the point. So at the left side and right side, you may see the different shear forces like that. You see? 여러분들 그 뭐죠? 수직력을 받는 빔 구조물의 전단력 선도 잘 생각해 보시면 점프업과 점프다운이 발생할 수 있죠. 집중 하중에 대해서 집중 하중이 작용하는 포인트에서는 그래서 왼쪽과 오른쪽 단면에서의 시어 폴스가 달라지게 됩니다. 점프업 또는 점프다운 때문에 그게 이제 프로그램상에서도 정확히 확인이 되는 거죠. Okay. So we can find the internal forces at everywhere. Okay, we can complete the first example. Also, as well as uh, the dimension of section, you can directly input the section properties. So please go to see. 너무 뻑되네. Okay, let's see. Go to property. I will explain how to directly input the section properties. If you click the create section again, let's make the profile here. Click create profile, and then you can select generalized. Then you can directly input the values. Let me see. And here you can input the sectional area, second moment of inertia, and torsion constant. So A is 6.72. I is here. Because we model the structure in 2D, obviously I sub 2 is not uh, affected or included. But anyway, you simply input the values. I2 is 6.2. And because this is symmetric section, product moment of inertia would be 0. And the torsion constant would be 2.4. And then go to the section manager. Please double click. Then you can change the section model. Then please go to job and submit again. As you could see, I make another profile of section and I changed the profile in the section model, predefined section model. And we can expect that the same result would be obtained because we input the same section properties to the model. Analysis was done. Because we did not assign the section shape, the program does not know what the section what the sectional shape is modeled, right? The program do not know, does not know. So the simple circle was assumed in the program. 우리가 이제 이 섹션 모델을 바꿨기 때문에 제너럴라이즈드 섹션 같은 경우는 값을 바로 집어넣어서 이 프로그램은 이 섹션이 뭔지를 몰라요. 그냥 값만 아는 거지. 그래서 렌더링 했을 때 이런 그냥 단순한 형태의 강봉처럼 그냥 우리에게 보여주는 겁니다. 근데 실제 강성형열에는 우리가 직접 집어넣은 값 자체가 들어가기 때문에 해석 결과는 똑같아야 되죠. 예. 아, obviously we did not check this first one. Let me see. Uh, here. Fortunately, I recorded this first one. How about that? Although there are very minor difference between the two values, we can conclude that although we directly input the sectional properties, the program show the same result. 예. 디멘전을 이제 직접 집어넣은 거하고 그다음에 우리가 그 계산 결과를 그 섹션 프로퍼티의 계산 결과를 집어넣은 거 결과는 정확하게 똑같습니다. 뭐 0.02 정도 차이가 나는데 이거는 이제 애초에 이거 그 섹션 디멘전 그러니까 치수를 가지고 이 값들을 계산할 때 뭐 반올림하고 뭐 이런 것에서 오는 차이가 이제 그 정도의 차이를 만드는 것뿐이지 뭐 결과는 충분히 신뢰할 만한 결과라고 보시면 됩니다. Let's check the reaction result. Alright, cool. How about that? The same result will be obtained. So you can choose the strategy. If you want to input the dimension of the section directly, you can select the predefined section. But please remind that as you can see in our program, there are limited section library. So let me see. Ah, here. There are limited section library. So if we want to model very specialized section, you cannot use this profile. Instead, you should input the calculated section properties by using the generalized option. Please mind that. Okay, then I gonna stop here today class. Then let me see. Now, so in the next class, in our classroom, we will take the second example together. So if you have any question or comment or some request about our class, then please send email to us. Then we will try to answer about your questions. Okay, I will stop here and see you in the next week.